In this demonstration, I'm going to write a calculation procedure for RK4 method for this differential equation, which is y prime equals y minus t squared plus 1 with the initial condition y of 0 equals 0.5. And we have to solve it from 0 to 2 interval. The exact solution is also provided here so that we can compare the numerical estimation and the analytical result. The RK expression, RK4 methods expression is written here. So it comes with the 4 K calculations, and then the value of variable y is estimated at a next step. So 4 calculations within a step are required, whereas we have the definition of these distinct Ks is in the block. So there are 4 Ks. So I reserve a column for the time step for time variable, and then I reserve 4 cells for distinct K calculations. Yes, okay. Everything is fine. So one cell for K1, one for K2, or K3, and K4, and they will lead to the numerical estimate of Y. So this is Y numerical. And I will also then calculate the Y exact and the error estimate for this problem. So I start with the time t equal to 0. And at this point, I have the initial condition, which is given as 0.5 for the problem. Okay. So for a step, let's define a step somewhere here. H equals 0.2. So for the first step, the step can be generated. Okay, I call it this value plus a value must be kept fixed in the further time step calculations. So time is the independent variable. So there is absolutely no problem. So K1 calculation, it requires the function to be evaluated at the first point, h f of ti yi. So it's an increment in y. So I will calculate like h times f of ti yi. So I have expression y minus t squared plus 1, where y and t must be calculated at the previous step, right? Which means if I am at I plus 1 step, right, point, then it should come from ti. So it is t y minus t squared plus 1. So y value is the old value of y minus t squared. So this is the t value, and I like it's squared and plus 1. So h times f of ti. Okay. H times f 2 minus a squared plus 1. Oh, okay. Well, I got the input from the students that the this taking square is not allowed. This should be done in a different way. Okay. Now the next step, h times, so again h, k dollar 2 times. Now this is important. So parentheses are really required if you are solving that one in Microsoft Excel. So y should be updated with the previous k value, right? Because y we have to provide here as yi plus k1 by 2, and t is to be provided ti plus h by 2. So I write here for y with the parenthesis. So it should be okay, the previous value of y plus k1 by 2. So it is k1 by 2. We do not require any other calculation on y. It is just y. So y to be replaced by y plus k1 by 2 minus t squared. So t is to be replaced by the value of t plus h by 2, which is k dollar 2 divided by 2, and we require its square. Square can be calculated like this, n plus 1, right? So this is the function evaluation at the uh, at the midpoint times the h value taken from the outlined cell here. Okay, this is fine. Now we have to repeat the similar kind of stuff for K3 calculation. Okay, so K3. So now it is equal to the h times k dollar 2 times the function evaluation. So first is y. Y is to be replaced by yi plus k2 by 2. So every y in the expression must be replaced by the previous y value plus k2 by 2. We do not require any further calculation. Minus t squared, and t squared will be replaced by the value of t plus h by 2, which is k dollar 2 by 2. However, we require its squared, right? Plus 1 in the whole expression, and that's it. In Microsoft Excel, it is rather tedious. It's very careful business to do that one. Therefore, we prefer the other programming languages where it's just a matter of providing the arguments to the defined function. Okay, K3 has also been calculated. Now, K4 calculation, it requires H. I have adopted that from the respective cell times the function evaluated. Function evaluated at the end of the interval, ti plus h and yi plus k3. So t must be replaced as ti plus h, and every y is to be replaced by yi plus k3. So now to the expression, I write the y value plus k3, and that's it, minus the t in the function, t squared. It will be the value of t plus h value. There is no divided by 2 here in the K4 calculation. However, I have to calculate the square because that is the function definition. Plus 1, and that's it. And now we are ready to get our estimate. So it is the previous value of y plus 1 divided by 6 times k1 plus 2 times k2 plus 2 times k3, right, plus k4 value, and that's it, This is the next value. And similarly, we can calculate for all the coming steps, but bit carefully. So this is here. Now the crucial step, compare it with the analytical result. So I compute the expression. It is t plus 1 squared. So t value plus 1 and whole squared minus 0.5 times e raised to the power t value. I'm successful. I think I have calculated the expression correctly, analytical expression. And now, well, let's do it a bit dramatic, in a dramatic way. I first calculate the error value. It is the numerical value minus the yardstick. In this problem, of course, we have the analytical result. And I first calculate this one so that every value seems to be horrible. And now the analytical expression. Behold, it is the most crucial step in this demonstration. Let's see whether I fall or swing with joy. Yes, the power of RK4 method. It has achieved the accuracy to 10 raised to the power minus 6, a scale of micro level. So now you can also consider the stability of the method. You can observe that one, right, through your algorithm. So if I go for a smaller step, then of course the answer would get more closer to the analytical result. However, if I go for higher value, right, uh, its accuracy is reduced. So you have to choose within your acceptable bounds, right? There is the only promise of numerical technique that with the smaller step size, you get closer and closer to the answer. So take a deep breath. It calms the mind. Adjourn.